Welcome to the Peacademia course on the basics of semiconductors. This lecture covers solar cells. Let's start. By the time you finish this lesson, you will learn solar cell structure, open circuit voltage of the solar cell, short circuit current of the solar cell fill factor, and the solar cell IV diagram. A simple PN junction to a large extent is an amazing device. Why? So far we've seen the PN junction used as a diode rectifying the electrical current, used as an LED emitting visible or invisible light when biased forwardly, and used as a photodetector when reversely biased. Indeed, we are facing with a device that can rectify, emit, and detect light. All these possibilities lead us to a step even further and ask a mind-blowing question. Can the PN junction generate electrical energy when exposed to the sunlight or any other light source? In other words, can we use the PN junction as an energy converter, converting sun or photon energy to electrical energy? Astonishingly, the answer to these questions is yes, and we can add another dimension to the possibilities we can achieve with a PN junction. In this lecture, I'm going to introduce solar cells to the extent that the schedule of this course allows. Discussing all the details related to solar cells demands a whole course, but I do my best to go over the most important basic concepts related to solar cells. In the lecture covering photodetectors, you saw this PN junction. We were interested in photons to cause generation in the depletion region. If you watched that lecture, you already know what I'm talking about, and if you haven't watched it, I highly recommend you to go back, watch it, and then come back to this lecture. If we look at the IV curve of this PN junction under no illumination, we'll get this blue curve, which is similar to any other diode we've seen in this lecture. Under no bias, the device is in the equilibrium and no net voltage can be measured at the device terminals. If I expose the device to a light source emitting photons to the surface of the P semiconductor, according to what I already explained in the previous lectures, the photon can generate a pair of mobile charge carriers, an electron and a hole, in the depletion region. Due to the depletion region electric field, the electron enters the N neutral region and the hole enters the P neutral region. Once this happens, the neutral regions are no longer neutral. In fact, they are ionized. So, if you connect a voltmeter across the device, you'll notice some electrical potential or voltage level. Since the device is not loaded, or in other words, it is open circuit, this voltage level is called the open circuit voltage V sub OC. If the photon flux P1, that is the cause of V sub OC1, is increased to photon flux P2, more generation in the depletion region takes place, and therefore the open circuit voltage increases to V sub OC2. On the IV curve, you can see where V sub OC1 and V sub OC2 are located. Let's consider another scenario. I disconnect the voltmeter from the device and short circuit the device terminals. What will happen? We already know that under illumination a number of mobile charge carriers are generated, and due to the depletion region electric field, they ionize the P and N neutral regions. Under the short circuit, the generated electrons in the N semiconductor leave the device through the ohmic contact and enter the P semiconductor on the other side from the ohmic contact. So what you can see here is a current flow. If the illumination strength becomes larger, the short circuit current gets larger. Therefore, if for the photon flux P1 we get I sub SC1, for a large photon flux P2, we have I sub SC2, which is clearly larger than I sub SC1. You can see it in the IV diagram. Clearly, under the short circuit, we get the largest current flow, and under the open circuit, the larger voltage level. But we gain zero power, right? Now, if I connect a resistor to the device, the voltage and currents are no longer I sub SC and V sub SC. In fact, they fall in between. Let me complete the IV curves of the device under the photon flux P1 and P2. If I divide this IV diagram into 4 quarters, to get some electrical power from this device, the device needs to operate in the 4th quarter. If I consider the device is receiving the photon flux P2, I can find a point at which the maximum power can be drawn from the device. The voltage and current associated with this point are Vm and Im respectively. For a solar cell, it is useful to define a figure of merit called the fill factor. The fill factor is the product of Im, Vm, divided by the product of Isc and Voc. You can consider the fill factor as the ratio between the area of a rectangle defined by Vm and Im to another rectangle area defined by Voc and Ioc. The closer the fill factor to 1, the better. This is the symbol we use to show a solar cell in circuit schematics. What we need to know is that the open circuit voltage Voc is smaller than the built-in voltage, and we already know that the built-in voltage is a small quantity. For example, for a silicon PN junction, it is around 0.7 volts. At the same time, the current produced by the device is in order of a couple of milliampere. So, not much of energy we can gain from a single device like this. To convert a considerable amount of photon energy to electrical power, we need to put devices in series and parallel. We need to put devices in series to increase the voltage level and put them in parallel to increase the overall current capacity. This structure is called solar panel. To absorb the most possible photons, the surface of the solar cell is made rigidly. This significantly reduces the reflection factor. In this lecture, I discussed the solar cell structure, open circuit voltage, and short circuit current of the solar cell fill factor, and its IV diagram. In the next lecture, I will introduce the bipolar junction transistor, or BJT. Thanks for joining this lecture of Peacademia.